Alright, let's just jump straight in here and work on these practice problems. So, 8.4 from the book says, consider this reaction. We have 2 aluminum reacting with 3 chlorines to produce 2 aluminum chlorides. If you begin with 0.552 moles of aluminum, and 0.87 or 887 moles of chlorine, what is the limiting reactant and theoretical yield of AlCl3 in moles? So we're trying to find the limiting reactant, and we're trying to find the theoretical yield. So what we're going to do here is we are going to think about what we're starting with and what it takes to find both of those things. So this is going to be a slightly simpler example because we don't have to go to grams. We can keep everything just in terms of moles. And what we're going to do to find the limiting reactant is we're just going to say, if all of this aluminum reacts, how much product is made? Well, according to the ratio, for every 2 moles of aluminum, we make 2 moles of aluminum chloride. Sorry for squishing all that in there, it just looked like a mess. But anyway, we're going to end up with the same number of moles here, 0.552 moles of AlCl3, because it's a 2-to-2 ratio, which is a 1-to-1 ratio. So that number doesn't change. So if all the aluminum reacts, that's how much aluminum chloride is made. On the other hand, if all of the chlorine reacts, so if we have 3-to-2 ratio here, for every 3 moles of chlorine, we make 2 moles of AlCl3. That I can't do in my head. Let me type that into the calculator real quick. That is going to be 0.591 moles of AlCl3. So, we just found, given those 2 reactants, if all of the reactant is used up, how much product is made. So what we're going to look at now is the smaller of the 2. Because what this tells us is that once the reaction produces this much AlCl3, it stops. The reaction can't make any more product because once we've made this much product, our aluminum is gone. It's been used up. So anytime we're trying to find the theoretical yield of something, what we're going to do, anytime we're trying to find the limiting reactant and the theoretical yield, because these 2 things are found simultaneously, they are not the same thing, but you do find them simultaneously, we're going to take the amounts of stuff that are reacting, figure out how much product can be made if all of it reacts, and whichever one makes less product, that is the limiting reactant. So in this case, the aluminum is the limiting reactant, and the amount of product that is made is the theoretical yield. So our theoretical yield is 0.552 moles of aluminum chloride. So again, we find the limiting reactant and the theoretical yield at the same time. You find them simultaneously, but they are not the same thing. They are related, for sure, but they are not the same thing. That's a very common mistake, as I will ask in a question, what is the limiting reactant, and someone will give me an answer that is actually true for the theoretical yield instead, or vice versa. So the limiting reactant and theoretical yield are found simultaneously, but they are not the same thing. Okay, let's look at another example here. So 8.5 says ammonia can be synthesized by this reaction. So we have 2NO reacting with 5H2 to produce 2NH3 and 2 waters. And the question says, what maximum amount of ammonia in grams can be synthesized from 45.8 grams of NO and 12.4 grams of H2? Okay, so we're going to do the exact same thing that we did in the last problem. Really what this question is asking for is the theoretical yield. It doesn't actually use the word theoretical yield, but it says what maximum amount of ammonia can be made. That's the theoretical yield. Theoretical yield is how much of this stuff can you make. That's the maximum amount. And so we are going to do the exact same thing. We're just going to say, okay, we have 2 reactants here. If all of them react, how much product is made? And whichever one makes less, that is the maximum amount of the product that can be made. And so to do this, we are going to use our handy 3-step process from back here, going from the mass of one thing to the mass of something else. So we're going to do our mass to moles, use the balanced chemical equation to go from moles of one thing to moles of something else, and then use the molar mass to find the mass in grams. So let's do that. And we're going to do that for both of these, for both of the reactants. So I can even pre-write in my slots for the conversion factors here, because I know I'm going to need 3 for each. The molar mass, the ratio, and then the second molar mass. So we can call this molar mass 1 and molar mass 2. All right. So that first molar mass is the molar mass of NO, which is going to be 30.01 if I remember correctly. If I'm doing it in my head correctly. Yes, 30.01. And again, that comes just straight from the periodic table. Nitrogen is 14.01, oxygen is 16, so put them together, you get 30. The ratio comes straight from this balanced chemical equation, and in this case, it is 2 to 2. So for every 2 moles of NO, we make 2 moles of ammonia. And then the last conversion factor is the molar mass of the ammonia. So that is going to be 17.03, I think. Let me see. Or 04, actually. Yeah, 17.04. So for every 1 mole of NH3, we have 17.04 grams. Okay. So if you go through and you check the units, you'll end up with grams of ammonia, which is what we want. If we do the math, 45.8 divided by 30.01 times 2 divided by 2 times 17.04 gives us 26.0 grams of ammonia. Good to know, but does not give us our answer. because we need to do the other one now. By the way, it's very tempting to assume that this is going to be the limiting reactant, what we get for this second one, because we have less hydrogen. But as we'll see, that's not always the case. So, same process as the previous one. Molar mass, ratio, molar mass. Hydrogen has a molar mass of, well, each individual hydrogen is 1. Sorry about that. H2 has a molar mass of 2.02 grams for every mole. The ratio is not 2 to 2, like it was for the previous one. This is a 5 to 2 ratio. So for every 5 moles of H2, we're going to have 2 moles of ammonia. And then lastly here, this molar mass is going to be the same as before. Because it's the same process. We're just converting from moles of ammonia into grams. And so you just copy that down from there. All right, so then we do that math. 12.04 divided by 2.02 times 2 divided by 5 times 17.04 gives me 41.8 grams of ammonia. So even though we started with a lot less hydrogen, because hydrogen is so tiny compared to nitrogen monoxide, we actually make more ammonia if all of that H2 reacts. Nearly twice as much. And so the maximum amount of ammonia that we can make from those reactants is 26 grams. That's the most we can make. We can't make any more than that. Because once we get to 26 grams, the nitrogen monoxide is run out, there's no more, and so the reaction stops. Alright, let's do one more of these practice problems. This is at 8.6. It says, consider this reaction. We have some copper 1 oxide reacting with carbon to produce 2 copper and carbon monoxide. When 11.5 grams of carbon are allowed to react with 114.5 grams, sorry for my sloppy writing there, 114.5 grams of copper 1 oxide, 87.4 grams of copper are obtained. Determine the limiting reactant, theoretical yield, and percent yield. So this is the whole shebang here. Everything that we could possibly find in this problem, we are going to find. So, even though it sounds really daunting, this is the exact same process that we did in the previous problem, just with one extra step at the end. The process of finding the limiting reactant and the theoretical yield, that's exactly what we did here. This was our theoretical yield, which means that the NO was our limiting reactant. So we actually did that in this problem. We're going to do that again for this one using the exact same process, only then at the end we're going to tack on the extra bit of finding the percent yield, since we actually were given an amount of product that was made. So this is what we would call the actual yield. So let's go ahead and do this. So just like before, we can set up our 3 conversion factor process here, since we know we're going to need 3 conversion factors. So for carbon, we have 12.01 grams of carbon for every 1 mole. The mole-to-mole conversion here, since we're trying to determine what the theoretical yield is of copper, since that's what we're given information on, that is a 1:2 ratio. So for every 1 mole of carbon, we make 2 moles of copper. And then the last mass, mole-to-mass conversion is just the molar mass of copper, which is 63.55. Which I did not know off the top of my head, by the way. I did just look at the periodic table. Okay, I'm actually not going to do the math yet. I'm going to go ahead and put these in first, and then I'll do all the math all at once at the end. So I'm going to do the same thing here with the copper oxide. So I need the molar mass of the copper oxide, which is going to be 63.55 times 2 plus 16. So I have 2 times the mass of copper plus 16 from the oxygen. That gives me 143.1 grams for every 1 mole. The mole-to-mole ratio is going to be a 1:2 again. So for every 1 mole of the copper oxide, I have, it's not 1, 2 moles of copper. And then this last conversion is going to be exactly the same. It's always the same. So for every 1 mole of copper, I have 63.55 grams. Whew, okay, so try to figure out where the edge of my screen is here so I don't write off of it. Okay, it's right there. So if I do the math here, 11.5 divided by 12.01 times 2 times 63.55, I will make 120, let's just round it to 121.7 grams of copper if all the carbon reacts. If, on the other hand, all the copper molecule reacts, so I have 114.5 divided by 143.1 times 2 times 63.55, I have 101.7 grams of copper. So what this tells me is my theoretical yield is 101.7 grams. Because again, the theoretical yield is the smaller of the possibilities. Once I make 101.7 grams of copper, I'm out. I have no more copper molecule left. It's not possible to make 121.7 grams of it because there's no more carbon, or no more copper to keep going at that point. No more of the copper molecule. And it also tells me that my limiting reactant is the copper oxide. So this is my limiting reactant here. So then the last bit, the percent yield, that is going to be equal to the actual yield, which we were told was 87.4 grams, divided by the theoretical yield, which we just calculated as 101.7 grams, times 100%. So if I do that math, let's see here. That is 85.9%. All right. I think we will call it there for this video. The last little bit here is just talking about a section that I'm leaving out of the video. So this is using enthalpy as a measure of a reaction. This is a useful process. It's a useful chemical investigative tool if you're trying to get information about a reaction, measuring how much heat comes off of a reaction to figure out how much of the reaction actually happened. But it's a little bit too specific, it's a little bit too niche, if you will, for what I want to get into here. So we're just going to leave it out from this video, and from this class. So that is it for Chapter 8. Congratulations, you made it to the end. You've made it through the stoichiometry. Now you just have to make it through the homework and the exam. So if you have any questions, feel free to email or to ask me the next time you see me in lab. Good luck.